Alrighty, so number one, what are the names of the type of radiation? Because this was the one I said my acronym really helps with this one.
Does anyone know this one?
Mine was, guys, the Disney uses very interesting makeup routines. That's how I remember it. So the G stands for gamma. And then what the X stands for? It's gammas, X-rays, U-rays, so ultraviolet. Visible, infrared, visible, and makeup and microwave. So these are the types of radiation. Do you guys know which is high energy and which is low? Energetic? Yes. So gamma rays is high energy and high frequency. So it means on the other side, should be the low energy. Low frequency. And then the long wave.
Yeah. So next one asks, what is the maximum number of electrons in the D subshell? Does anyone know this one? Want to give it a shot? Yep, it's 10. Because we have SP2, P6, and D10. Good job.
All right, good job. Number 3, so an electron on the third level, what are the possible quantum numbers? So we know it's on the third level, so n, the principal quantum number, is going to equal 3. Know that right off the bat. The angular is L. Do you guys know how to find that? N minus 1 also. So it's going to be 2. Right? And then the next one, remember, we're going to go plus to minus the L. So the possible answer, that would be negative 2, negative 1, 0, and 2. If you notice as well, n equals 3, right? We know that that's a d orbital. There's 5 orbitals, 1, 2, 3, 4, 5, and each orbital can hold 2 electrons, right? So that's how we can get the 10 from the previous question. Last but not least, the spin quantum number. I always like that one because it's always going to be the same. You can either have plus or minus 1/2. Does that make sense?
Okay. Next one says, as we move across a period from left to right, the atomic radius. Yep, it does decrease. Does everyone understand that part? Because remember, atomic radius is going to go from this way, then down on the periodic table.
Okay. And kind of corresponding with that one is number 5. Cations are blank, then their corresponding neutral radius. What do you guys think?
It is smaller.
Good. Oh, and that is because they have less electrons, right? But then the nucleus of the neutral stays the same. So the electrons are held more tightly by the protons in the nucleus here because they have less electrons. Then the opposite is that anions, which would have more electrons, would be greater than their corresponding neutral radius. So perfect. A, smaller than.
Okay, for 6, this is my last quiz from last year. So it says, of the following choices, which would you expect to have the most negative, which is like the most exothermic electron affinity?
Number electron affinity. Just like ionization energy and like electronegativity.
Remember, when it's exothermic, it's losing. So it's going to be negative. Any guesses? It is not lithium.
You want to expand a little bit more on?
So here would actually be fluorine. Fluorine here would be the most electronegative. So how like I was explaining last year is that the exothermic, it's exothermic, right? So it's gonna be negative. So it's like the change of energy must be negative. So remember that the definition of electron affinity is energy released. So it means that the reaction is exothermic. And if the reaction is exothermic, it's negative, which means that the electron affinity is positive. Does that kind of make sense? You probably won't see this, but I was just like to get y'all thinking. How I just like looked at it is if you look at the periodic table, I saw which one was the farthest one over. and the highest one up, is how I thought about it. Because I know helium isn't going to want to donate, but fluorine would. There you go.
Okay. So the ground state configuration and shorthand for Ti2 plus. So we're gonna copy and paste the periodic table. Let's put it up there. Okay. So first find titanium. Ti. Ti is right here, right? But we're looking for the 2 plus. So does that mean we have 2 more electrons or 2 less electrons? 2 less electrons, perfect. So instead of going this way 2, we're gonna go this way because we have 2 less electrons. So 1, 2, we're gonna get the configuration up until here. Okay. So let's first start with the S. 1, 2. Open the first row. 1, S, 2. I'm going to go to the second row. This is 2s2. This is the P block. And all of those are used with 2p6. And then we're going to go with 3s2. And then 3p6. And then, like I said, we're going to only go up to this one. So 4s1, 2. There's so that's the ground state configuration. Now the shorthand, remember what we do is, although we're still finding right here, we got to go back and find the previous noble gas. So if we go back, it's going to take us to argon, right? So we're going to put that in parentheses. That just means we are starting from there. So starting from there, in configuration, we're just going to keep going from here instead of writing everything beforehand. So that's called the shorthand. So if we just start there, we know it's 1, 2, 3, 4. S. And that's it. Does that make sense, everyone? Perfect.
Okay, the next one is writing an orbital diagram for carbon. So we know that carbon is over here. So we have the 1s orbital, we have the 2s orbital, and we also have the 2p orbital. Each one gets a little box. So we have 1, 2. So we have 1 up and 1 down. Remember that you have to put 1 in every box for that orbital before you can move on to the next one. We also have 1, 2, 2s2, and then we have 1, 2 of the 2p. Everyone gets that part? Okay, cool. It shouldn't be left, couldn't be left empty.
It can be left empty depending. So Hund's rule is that you can't fill up these in one first. So with this, we had to do the only 2 because over here, carbon is only 1, 2 into the 2p6. So you only had 2 electrons to put in. It can be left empty. What you can't do is this. You can't, because according to Hund's rule, you can't do it like this. Because if I put another one, let's say we filled this up, it wouldn't be carbon anymore. Now it'd be you're finding it for nitrogen. If you can count these, you see 1, 2, 3, 4, 5, 6, and carbon has 6 electrons. Remember, we're counting electrons in this. Does that make sense? So that's candy that's empty. Okay. What happened in there?
Okay, so in my lab, we had to do carbon, and he told us to write it 1s2, 2s1, and 2p3, so our diagram could match. So you said it depends on whose law we're using?
So that he made you do 2s1 and 2p3.
Yeah, that's what Saha said.
I can double check with Lisa. I don't want to give you wrong information. So let me double check that.
Okay.
And I could send it because this is what I know it as. The only exceptions to these rules that I know of is copper and wait, what was it? And CU.
Okay.
So, I would on her
yeah.
tonight and ask her the question too.
Right. All right. Thank you.
Of course. This was just on
Maybe
one of our yeah.
Send us the picture of the question where like he asked you to write it, because maybe it's like asking something different. Because I don't think I don't know. Like, I think the only exceptions I've seen.
Which lab are you talking about from Saha? Because I have them.
It is the, let me see if I can find the title for it. I do not have the title for it, but the question just asks us to write the electron configurations for the following atoms and draw the orbital diagram. So when
or is that the workshop for it?
That was a workshop for it.
Gotcha.
But I can ask the professor tonight.
Okay, I'm looking at my stuff and I don't.
Okay.
Okay, because even when I look it up online, like the orbital for carbon, the same thing that we put comes up. But I'll see if like, if the professor told you that, then yeah, I definitely want to double check and see if maybe they're teaching you a different way. Because I know like maybe if you're adding energy, you can make it 2s1 and 2p3. That's interesting. So yeah, I will definitely double check. You said no worries. Okay. Okay. Number 9. Which of the following occurs, the energy of a photon increases. So remember with our gamma to our radio wave, which had a high energy? Gamma or radio? And I'm going to in between, but those are the endings. Remember this?
Are you talking to me?
No, everyone.
Oh.
Anyone know? Which is has higher energy, gamma rays or radio waves? When I think of this, I say high gamma, like you say hi to your grandma. Or you can think of it another way, but hi grandma. And then when you're turning off your radio, because radio waves is the R, I'm like, ooh, can you lower the radio? So low radio, high gamma. So gamma waves has high energy, right? If you have high energy, so that means if we're going this way, as energy is increasing, remember we also have a high frequency. So that's gonna get this out. Do we have a long or short wavelength as energy is increased? The way I remember this is, like I said, for radio waves is low energy, low frequency, long wavelength. It's like I, and L, right? So then that would make that this would be a short wavelength. So it's going to be. Does that make sense? So remember L and L, low energy, low frequency, long wavelengths with radio waves. As you get closer to radio waves, and as you get closer to gamma rays, energy increases. And so high energy, high frequency, short wavelength.
Okay, for number 10, it asks you which orbital is closest to the nucleus. And how I like to think about it is how I start off with the orbitals or even the configurations. So I like to do just automatically start writing it out. So there's 1s, which is the closest. You have 2s2. So then 2s. Be your answer here. You're correct. So be 2s. So but it was asking for the farthest one. It'd just be the opposite. S2, 2p, and then you can keep going. Okay, cool.
So the next one is called identify the color with the wavelength of 540 nanometers. So which of the radiations has what light has it? What kind of light? So this is all of them together. Which of these rays has stuff we can see, has color we can see? It can kind of be self-explanatory, I guess. But visible light, right? Visible light, visible color. So just, obviously you guys know Roy G. Biv. It'd be okay. So red light has a wavelength of about 700 nanometers. And then violet has one of about 400 nanometers. So if you're asking for 540, that's about right in the middle, right? So that would be the green. The green has anywhere from about, I'd say 500, 510 to about 550. This part thing is also in your guys' notes that I think is really good for you guys to memorize it. And if you can see 700 nanometers, that's like a longer wavelength, right? As opposed to the short wavelength of 400, like how we know that the gamma is short. That's why I wrote it like that. Does that make sense? So 11 would be, this is green at 540. Any questions on that one? Also, I know you guys had a quiz yesterday. Do you have any questions from what was on the quiz as well? While we have you here. So we can go over it too.
I don't think that she released the quiz answers, but I know that I got 2 wrong. I'm gonna double check again to see if she released them, but let me
Okay.
see really quick. No, she didn't. She doesn't show which ones you got wrong yet.
Okay.
I'm zoom out.
Okay. If you remember what the question is, or like there's a similar one, just let us know, okay?
Okay.
If you remember. Okay. And then you want to go over this one?
So place the following in decreasing ionization energy. So we have CS, which is the final periodic table. Over here, we have argon and magnesium. Does anyone want to draw on the screen about the ionization energy pattern? Anybody? So we're going increasing and we're increasing, right? So if we're place it in order of decreasing, what do you think it would be? It is not D. It is E. Good job. Now, how I like to think about this one, so argon was the highest one, right? So we know this is the first one, so it has to go last. Or it goes first, right? Because this is number 1. Magnesium was number 2 and 3. So all I would do is 1, 2.
Yeah, and I know too that these questions do kind of try to trick you when it says in order of decreasing IE. So always look up for that as well as asking, because if you look at this next one, this one says increasing. So again, look up for that. So going into this next one, place the following in order of increasing atomic radius. So atomic radius increases down, and it increases this way, right? The opposite of everything else. So atomic radius, if you know atomic radius, you know everything else, because everything else is the complete opposite. Ionization energy, electronegativity, electron affinity, everything else goes up and to the right. This goes down and to the left as it's increasing. So let's see what we're trying to find. Chlorine is right here. Okay. Phosphorus is right here. Down here. So what I like to do is say increasing atomic radius. So we're going to start with the least one, right? And we see chlorine is all the way over here. So we need to know that chlorine is smaller than phosphorus because of the way that it goes increasing to the left, and phosphorus is to the left of chlorine in the same row. So we know that chlorine is the least. So chlorine is less than phosphorus. And then Ba is all the way over here. So we know it's further down in the column, so the bigger atomic radius, and it's more to the left. So in order of increasing atomic radius, it would be Cl, P, and Ba. So that would be B. Does that make sense? Any questions on that one?
I think I have that, the question they're asking about. I'm gonna add it to the doc here in a second.
Okay.
It's just, it's talking about like the calculating the emitted photon when an electron moves from like one level to the next.
Okay. That one's from the quiz?
Yeah.
Okay.
So it's like 17 actually.
Okay.
Yeah.
Okay. Cool. Okay. Do you want to go over the next one? Me too.
Yeah. So 14 is asking for n equals 3, what are the possible orbitals?
And remember, n is the principal quantum number too. Do you guys know what that tells you, the principal quantum number? It tells you the size of an orbital, right? So n equals 3, that's going up to the d orbital. So that just tells you how many, the size of it. So you know what each thing size is, each quantum number.
Okay. For the next one, it says calculate the wavelength of a baseball moving at 32.5. So we know we're looking for the wavelength. So I put wavelength equals h over mv. So I like to plug in for x. So we know that the 6.68 times 10 to negative 34 is a constant.
Got that number?
What?
I said, does everyone know if you got that number and what it's called?
No. Go over that. I pull back up my notes. Nevertheless.
I just think they know it's called Planck's constant.
Which is, there we go. Which is 8. And then we know, because this is in grams, I'm going to convert to kilograms. So it would just be 0.155 kilograms. So 1.55 kilograms. And we have 2.5 meters per second. So everything equals, see if y'all get it. Just make sure you do the parentheses correctly in this math problem also.
And make sure what you're doing here, you're converting it to kilograms.
Yep. So here,
Less than a minute. So why don't we log off and then get back on? And once we get back on, we'll share the answer, okay? Does that work with everyone? Alrighty. Yeah,